Welcome everyone. Continuing real numbers. Let's see what is second theorem. Fundamental theorem of arithmetic. Any number can be written as product of smaller numbers. Let's say 40 equals to 4 into 10. We can further make those smaller numbers as prime numbers because prime numbers don't have any other factor than itself and 1. So our 40 equals to 4 into 10 becomes 40 equals to 2 into 2 into 2 into 5. Or 40 equals to 2 to the power 3 into 5. What theorem says is every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occurs. So we can write 40 equals to 5 into 2 to the power 3. That order doesn't matter as these two are unique for 40. Now how to apply this theorem? Let's see a problem. Consider the numbers 4 to the power n, where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. For a number to end with digit 0, it must be divisible by 10. Okay? Or it must be divisible by 5. So now, let's see what 4 to the power n looks like. It is a multiplication of 4 to n times. So if 4 is divisible by 5, then so is 4 to the power n. Let's prime factorize 4, which gives us 4 equals to 2 into 2. It doesn't consist 5 as its prime factor, and thus it's not divisible by 5 too. So we can say 4 to the power n does not ends with digit 0. Now let's see how to find LCM and HCF by prime factorization. Let's take two numbers, 6 and 20. So you can see the prime factorization of the numbers. 6 have 2 and 3 and 20 have 2 to the power 2 and 5. Now the HCF is product of smallest powered common prime factor. So here the common factor is 2 and smallest power is 1. So the HCF is 2. LCM is product of greatest power of each prime factor involved in the number. So we have prime factors 2, 3 and 5. And their greatest powers are 2, 1 and 1. So LCM is 2 to the power 2 into 3 to the power 1 into 5 to the power 1 equals to 60. The method is same for three numbers taken together. Now there is another relation of HCF and LCM, which is for any two positive integer a and b, HCF of a and b multiplied by LCM of a and b equals to a multiplied by b. Try yourself for 6 and 20. Let's revisit irrational numbers. And here comes our third theorem. It says let p be a prime number. If p divides a to the power 2, then p divides a, where a is positive integer. Let's see how we will apply this theorem. For example, let's prove theorem number 4, root 2 is irrational number. We start by assuming. Let's assume root 2 is rational, so you can write root 2 equals to r by s. And if r and s has common factors, by dividing we will get a by b, where a and b is co-prime or don't have common factor. Like suppose r is 6 and s is 4, so common factor is 2, and by dividing we get a equals to 3 and b equals to a by b. So again, coming back to question, we have root 2 equals to a by b. So b root 2 equals to a. Squaring on both sides and rearranging, we get 2b square equals to a square. Therefore, 2 divides a square. Now by the third theorem, it follows that 2 divides a. So we can write a equals to 2c for some integer c. Substituting for a, we get 2b square equals to 4c square. That is, b square equals to 2c square. This means that 2 divides b square, and so 2 divides b, again using third theorem, with b equals to 2. Therefore, a and b have at least 2 as a common factor. But that contradicts the fact that a and b have no common factors other than 1. This contradiction has arisen because of our incorrect assumption that root 2 is rational. So we conclude that root 2 is irrational. So you can try this for root over 3 also. Let's visit decimal expansion again. Our fifth theorem says, theorem number 5, Let x be a rational number whose decimal expansion terminates. Then x can be expressed as in the form of p by q, where p and q are co-prime and the prime factorization of q is in the form of 2 to the power n into 5 to the power m, where n and m are non-negative integers. For example, we can write 3 by 8 equals to 3 by 2 to the power 3. Multiplying 5 to the power 3 on both numerator and denominator, we will get 3 into 5 to the power 3 divided by 2 to the power 3 into 5 to the power 3, which gives 375 divided by 10 to the power 3, which is 0.375. Our sixth theorem states, let x equals to p by q be a rational number, such that the prime factorization of q is of the form of 2 to the power n into 5 to the power m, where n, m are non-negative integers. Then x has decimal expansion which terminates. So we can say if the decimal expansion terminates or not without dividing. For example, 3 by 5 can be written as 3 into 2 by 5 into 2, thus decimal expansion is terminating. Now our seventh theorem, let x equals to p by q, where p and q are co-primes, be a rational number such that prime factorization of q is not of the form 2 to the power n, 5 to the power m, where n, m are non-negative integer. Then x has a decimal expansion which is non-terminating, repeating, recurring. For example, 5 by 3, where q equals to 3, cannot be written as 2 to the power n into 5 to the power m form, so its decimal expansion is not terminating and repeating, as you can see in the screen. Now you can solve the exercise. Don't forget to complete the task given in video. See you in next class.